Good evening, students. Welcome to another session of JEE advanced classes, my classroom classes, chemistry. So today, actually in the last class we discussed organic, we started with organic and we discussed the general organic chemistry already. So now we are going with the next, let us say the compounds in organic molecules, and that we just start with now the hydrocarbons, means only we just cover, let us say alkanes, alkenes or alkynes, those things are benzene related compounds. These topics we just covered today. Okay. So let us see again through the just basic applications we just cover now. So let us see. In which of the following hydrocarbons there is a DL pair which is formed on the catalytic hydrogenation to give an alkanes. So during, let us say, any catalytic hydrogenation, how the process takes place, what is the stereochemistry aspect. So whenever we just consider the chemical reactions in organic, mainly the mechanistic approach and the stereochemistry of these compounds is very important, that what we should learn. So when we consider now, suppose this type of compounds which are given here, what is this compound that is given to us is nothing but this compound has hydrogen here and hydrogen here. So the given compound having ethyl groups and ethyl groups, suppose even if it is not ethyl and ethyl, then we say this compound is nothing but having hydrogen and hydrogen which are opposite. So we call this isomer as trans isomer. So when we consider this now, when we are doing the hydrogenation, catalytic hydrogenation, so during the addition of hydrogen to a carbon double bonds or triple bonds, where the catalytic hydrogenation, hydrogen is added on the catalytic surface, how that will be added? So if you just see a carbon double bonded system, which is generally like a planar completely, even a triple bond, which is like linear molecules. So when you are adding hydrogen to them, how hydrogen gets added? So the process is like what we just say, the process is under, let us say, catalyst if you use. So the alkene or alkyne molecules reach the surface of the catalyst where the hydrogen was adsorbed already. So this alkene also gets adsorbed onto its surface. Then there is a simultaneous bond cleavages and bond formation, that is through a transition state, the hydrogen bond is cleaving simultaneously, carbon multiple bond, double bond or pi bonds are cleaving, then the hydrogen and carbon bonds are forming. So how the hydrogen gets added to any compound? So the addition of hydrogen always proceeds through, let us say, as a transition state. So H and H, these bonds are cleaving, this bond is cleaving, forming, this carbon bond is cleaving. So what we see, the addition of hydrogen takes place from the same side. So what we are getting, hydrogens here. So the addition is what we say syn addition. So when we consider any molecules, if the hydrogenation process is there or catalytic hydrogenation process is there, the addition is a syn addition. So for the trans compound, if you are adding the molecule or hydrogen through syn, then what we see? So if you just see in the next page, we see, and we'll come back to this question now. So if you have an alkene or addition, then what you try to do always is write the molecule like little bit inclined, like a Sahas type representation. But hydrogen we are adding to this compound from same side. So this compound finally converts into this way, that is C. You can say, or let us write only instead of C, let us write a simple line symbol, so line representation. So hydrogen is added from here, hydrogen is added to this carbon from here. So the groups which are already there, they move like upwards. So the hydrogen is adding from the down. The groups which are in the plane, they move like this. So if we just take the compound with this configuration, let us say like CH3 hydrogen, let us take only the given one already. So what was the given one? Was trans, first one. So C2H5 here, C2H5 is here, hydrogen was here and hydrogen is here. So now what is this one will give? So let us, so this compound will not give for us. So let us make this change a little bit. This is, suppose we have CH3 and CH3. So in a point of view, that is where the hydrogen is added in a syn addition to the trans molecules. So this is a trans. We are adding by syn path. So what is this is now? The C2H5 and CH3 which were like this, they move like this in the same direction. So CH3 is on the right hand side, C2H5 is on the left hand side. Here CH3 on the right hand left side, this is C2H5. So what is this Fischer projection for this? It's a simple thing, holding this molecule simply like this. That is what we already discussed in the previous class. So when you have a Sahar's representation, if you hold this molecule like this, simply it converts into Fischer projection, because both are having this like Y type symbol. So the groups which are in this way, they come towards us, and the group which is downwards will move backside. That is a Fischer projection representation. So we have H here, CH3 here, C2H5 here. This will become a top carbon, this will become a bottom carbon. So this will become a C2H5 and this is a CH3. But this compound does not have plane of symmetry. So what we say, if hydrogen we are adding, we are getting like this. But hydrogen we can add from the top side also, means the molecule is like this also, it is coming. So that hydrogen is we are adding from the down, this carbon from here, our catalyst can be like this. So molecule can come like this, catalyst can be like this, it can go like this. So the hydrogens get added from the two sides. So even you will get a mirror image of this. So what is its mirror image is C2H5. Because when you are adding hydrogen from one side, you are getting this type. When you are adding hydrogen from the opposite side, you will get the just opposite type configuration. So what do you see? This compound is optically active because it has C2H5, CH3, CH3, C2H5, H, different groups at two different carbons. So this is, suppose if you assume D, this becomes always L. That means we get racemic mixer. So for the trans compound, when you are adding syn addition, we get racemic mixer. But when we should apply these abbreviations, this is only applied when at the carbons, the groups are completely same. Because when we take the cis compound, that is CH3, CH3, C2H5, C2H5, if you are adding the hydrogen under the catalytic surface, nickel or something, then what do we see? The Fischer projection formula for that I can write simply like this: H, CH3, C2H5, CH3, C2H5 and H. So what is this is? It has a plane of symmetry, internal plane of symmetry. So this compound we say is a meso compound. But even you are adding from the top, then also we get meso only. Means even you take its mirror image. So C2H5, CH3, C2H5, CH3, hydrogen and hydrogens. So both these compounds are nothing but only meso compounds. They are not different compounds, they are the same. because the groups are same. Whether you go in any direction, your position of the carbons is same. Means this carbon may be a second carbon, this carbon may be a, so one, let us say 1, 2, 3, 4, 5, 6. So it is 3 and 4 dimethyl. So this may be 3, this may be 4. Otherwise, this may be 3, this may be 4. Because you can number from this end, you can number from this end. So this carbon you can't fix as 3, this carbon we can't fix as 4. So what we say? The two carbons are different and are same completely in either of the direction. That's why we say the compound is only a meso compound. So cis compound on syn addition is giving meso. So the same abbreviation we also use in case of the elimination cases or any cases where racemic mixer with a syn elimination will give trans compound. Meso compound with a syn elimination will give cis compound. Similarly, addition we are doing by antipass also sometimes. So it's a just a completely reverse order. So we said TSR. Similarly, we can say TAM. Here we can say CAR. So you have to remember only this thing, which is car. So CARTAM. Similarly, if you say anti, this is the order. If it is syn, the reverse. For CAR we are getting, for TSR. So when you are changing this, you have to change this. So I think, suppose we go with the question now. What is that? So a trans compound, when you are adding hydrogens here, so anyhow, you don't get an optical active. So this cannot be your option anyhow. Maybe sometimes multiple correct questions, multiple options are there, maybe. Let us see that also. Now here we have C2H5, we have C2H5, we have CH3 and CH3, that is what we started and discussed. So what is in this case now? Hydrogen comes here or hydrogen comes here. And what is this isomer? This is again only trans isomer. So trans isomer means you are adding syn. So you will get again racemic. Clear? That means he is asking DL pair you will get. So that is, this can be our option. Now what is this? This is a cis compound, CH3 and CH3. Either these two groups may be same or different, but at least this CH3 and CH3 are same. So this is a syn compound, cis isomer, sorry. So cis isomer with the syn addition will give meso. But anyhow, this compound will not give meso because completely the groups are not same. So here you can't use that abbreviation. Clear, I think? Because here there is a CH3 and CH3. This is an isopropyl group. And here it is like an isobutyl group. So the complete groups are supposed same. Then only we can use that an abbreviation as CARCSM. But in this case, you will even get now cis compound on syn addition ఇట్లా చూడాలి మళ్ళీ ఎవరైనా okay students, there was a mic problem. Sorry. So now any polar groups will be converted to non-polar groups because the red phosphorus HI behaves like a strongest reducing agent. So this is also converted to now the same. So we also say this is also the same. So all are giving the same final product. Clear? Now coming to the next question. So there is a space given for us. Now the same deuterium we are adding under palladium. So already what we discussed this thing. So what is this? It's a trans compound. We are doing hydrogen or deuterium under catalyst surface, that is syn addition. So you are getting this compound which is given CH3, CH3, deuterium, deuterium, there is no plane of symmetry. So this compound is optically active, this compound is optically active. So we say this is suppose D, this is L. So you are getting a mixture of D and L, resuming mixture. So which is correct regarding the equations. So the first one is correct. Trans compound, syn addition is giving a resuming mixture. But lithium aluminum hydride you are using. So all these are like preparations of alkane mainly if you just take it. So in this case, lithium aluminum hydride when treated with tertiary alkyl halides. So tertiary alkyl halides with a hydride donor which is like a strong hydride donor like lithium aluminum hydride which is supplying the H minus. It's the strongest hydride donor. So the H minus will behave like a stronger base also. It's not a bulky base, it's a smaller and it is a stronger base because its conjugate is very, very weak acid. So this one is a stronger base also. So this tertiary alkyl halides will generally favor elimination. So with the tertiary alkyl halides, it is not a possible case to substitute or replace it or to undergo substitution reaction. So only tertiary will give substitution reaction under the neutral cases. Means when you use water, you can write Br with OH. Alcohol, we can replace the Br or halogen with OR. So that is only the possible with the tertiary. But tertiary alkyl halide with the lithium aluminum hydride will give actually alkenes. That is CH3, CH3 and double bond CH2. Next, this is the red phosphorus HI. So already just now we said, so this cannot convert into alcohol. Means this one is converting directly red phosphorus HI with the acid, it is directly giving alkanes. So CH3, CH2, CH3. But to get alcohol, what I should do? The acids, if you want to reduce into alcohols, we can use lithium aluminum hydride. Or acids can be even reduced with diborane in THF. So the acids will give the primary alcohols. Okay. So this is possible with a hydride donor like lithium aluminum hydride, but sodium borohydride cannot reduce again acids, but diborane can reduce it. So mainly the reducing agent which we use for the reduction of acids is lithium aluminum hydride or diborane in THF. Okay. So this is wrong. So this is wrong. Next, bromine in presence of which? So bromination process is the radical process. So where you are seeing the radical formation, at this carbon we don't have a hydrogen, but this carbon has only hydrogens. If there is a hydrogen here, there is again still a bromination possible here, because benzyl radical will form there. Because phenyl adjacent carbon is a more stable with a radical formation, which is called benzyl radical. But this carbon now will have a radical formation. So at this position, there is a radical formation. So the Br can come at this place. So this is like generally we consider normal or radicals. So free radicals are generally planar type, sp2 hybridized type. So there is a pure p orbital left with an unpaired electron. So what we see, the bromine when it is coming at that particular place, it can approach for the planar molecule. Bromine can come from above, bromine can come from below. So at this carbon, when the bromine comes, it will be the two possible cases. But here the carbon configuration should not change. So here the carbon configuration is retained. pH is above the plane, Br is below, CH3 is in the plane, CH3 is in the plane, Br is below the plane, pH is above the plane. So at this carbon, the configuration of the carbon is retained. So but only that Br which comes here may come above the plane or below the plane. So these two possibilities that you will see. That means this is also true. I think clear this one also. Okay. So lithium aluminum hydride with tertiary alkyl halides cannot give substitution. So next. Now this one, just see carefully, and this part is not a D, it's just a thing. It's an elimination, heating. So let us see what will happen. It's an alcohol. We are heating with concentrated H3PO4. So which type of acids generally we use for the dehydration of alcohols? The acid conjugate should not be a better nucleophile also. So we can't dehydrate the alcohols by HCl or HBr or HI. Generally they are dehydrated only through concentrated H2SO4 or concentrated H3PO4, where the conjugate of these acids, that is HSO4 minus or H2PO4 minus, these are weak nucleophiles, so that they cannot be generally easily substituted when the OH group becomes a good living group because of the protonation process. So what we see? First, H plus reacts at this. So we just suppose write, and then we will come back to this and see. So we just completely transfer this molecule into the next page and we will see the mechanistic path. So we have a 6-membered ring with a double bond here. Then if you see the structure 1, 2, 3, 4. So at this 4th carbon we have all the CH3 groups. So 1, 2, 3, third carbon has a OH group. So 1, 2, 3, 4. So there is a CH3, CH3, CH3. So use just a normal thing. This is a OH. So when we add H plus, so the protonation takes place at this. So this will convert into But water is a good leaving group, it leaves. But we have a tertiary quaternary carbon at this. So we first initially get a carbocation from here with the loss of H2O. But one of the methyl group shifts from here to here. So one of the methyl group shifts. So methanide shift takes place. So this carbon so one of the methyl group is shifted here. But there is an internal nucleophile, that is an alkene or a double bonded carbon. So this carbon which is acting like a nucleophile, so this carbon with a already internal electrophilic carbon or positively charged, this pi bond will shift. So when it is shifting, generally it shifts towards this carbon, because when you get positive charge here is better. So this carbon is becoming negative and this pi, positive charge, this carbon immediately reacts. Or this electrophilic, internal electrophilic addition takes place. So this internal electrophile will be added at this double bond. So immediately we are seeing a formation of another cyclic thing. What is the ring structure? 1, 2, 3, 4, 5 and 6. So we have another 6-membered ring here. So whenever you write like a ring structure, what you try to do is write numbers 1, 2, 3, 4. So excluding this, we have 1, 2, 3 and 4. But fourth has 2 methyl groups. Third has a methyl group. But now this carbon is getting plus. So this is a tertiary already. Now do we have any possibility of further rearrangement here? This may go to here, it will become again tertiary only. But that is not a stable one. So there are only 2 tertiary carbons, remaining all are secondary with respect to this carbon. So it may go here, only possibility, it will not go ever. So it may be a tertiary, that is what you try to see whether it is rearranging there maybe. No, because from this tertiary it goes to this tertiary, this carbon with the positive charge is less stable than this carbon. Because at this carbon, there are 2 hyperconjugatable hydrogens here, 2 hyperconjugatable hydrogens here, 1 hyperconjugatable hydrogen. But if suppose you imagine the positive charge at this carbon, maybe sometimes the idea may come because there is again a methyl groups here, there is a rearrangement again maybe. So this carbon with a positive charge has less number of, so 2, there is no hyperconjugatable hydrogens here, there is only 1. So there are 3 hyperconjugatable hydrogens in this. But in this there are totally 5 hyperconjugatable hydrogens. So this is only the stable thing. So what you see now here? There is only the loss of H plus again, because it is completely a dehydration acid catalyzed. So this oxy just C. Just say So we get now double bond may be here, double bond may be here, double bond may be here. But with double bond is more stable. Means again you have all these possibilities. So you check again where the double bond you may see. So if you are saying a double bond is formed here, suppose one possible case, the double bond may form here. Because with respect to this carbon, alpha position you will get a double bond, or alpha carbon hydrogen here, or alpha carbon hydrogen here, alpha carbon hydrogen here can be lost. So double bond you may see here, double bond you may see here, means plus. So this plus is not a charge, just careful. So you are getting the plus or and you see. And also you may get this. So is these two are same? No, different. Because you can number the carbon chains here. So this is 1, 2, 3, 4, 5. Here it is 1, 2, 3, 4, 5, 6. Or if you go like this 1, 2, 3, 4, 5. So which is better? If we write number 1, 2, 3, 4, 5, 5, 5. So 4, 5, 5. If you go like this 1, 2, 3, 4. So this is like a numbering system. Just one you are going it. From the bridged head to this, you are going like this. From bridged head, you are going like this. So which is a better thing? You can't start from here. You can start from here, bridged head. Similarly here, 1, 2, 3 like this. So these are different actually. Because in this you are going to this carbon to this. So this is the major one. Because it has more. So 2 hyperconjugatable hydrogen, alkene with more number of hyperconjugatable hydrogens will become again more stable. So the major product for this process is a double bond should exist between the two rings. So let us see which option is there for us there. So this one. So there are only 2 given, but anyhow that will not be there. So this is our option for us. Okay. Now coming to the next. Which of the following is deuterated 1-bromo 2-methyl cyclohexane undergoes E2 reaction? Then the product formed is. So in a cyclohexane we always generally say, so there is a cyclohexane. When you try to represent this in the form of cyclohexane exists in a chair form and board form. Chair form is more stable. So when the E2 process is happening in the cyclohexane, in the chair conformation, so in which way, just let us write in the next page again. So here, if it is a chair conformation, then what you see, the axial bonds exist completely anti-periplanar. So the groups which are living during the E2, because the simultaneous pi bond formation starts. So both the living groups must be always in diaxial position, anti-periplanar position. So even if it is a, let us say what is the equatorial position, then equatorial position may be above and below, but they are not completely anti-periplanar. Because at the particular down carbon, group is like this. At the back carbon, the group is completely like this. Means it exists like this, in this form. But at the above, it exists like this. So both these are not completely in the same plane. So it moves downwards like this. It moves upwards like this. So these orbitals are not completely in the same plane. But if it is diaxial completely, they can form pi bond easily. So when we try to represent that structure, so what is the structure that we had? Let us see. H, CH3, Br, H, D and H. So this is the thing what we had. H is above, CH3 is below here. Here Br is above, I think. Hydrogen is below. We will change it if it is not the same. Here D is above, hydrogen is below. Let us say is it the same? So only change is here. H and CH3 okay, Br and H is okay, D and H. So here there is a slight change what we should do. So here it is D and H. You think no? Same. H is above, D is below. You can write any left side or right side, that is not an issue. But when we convert this into the chair conformation, suppose assume this is the Br, is this carbon. So I assume this carbon is 1, this carbon is 2. So like that if you go on doing it, it may be a 4, oh, sorry 6. So what we see, this chair conformation of this. So I write the chair conformation of this, assuming this as 1, that is Br is above. So when a group is in the above wedge symbol or dashed flying wedge symbols, solid wedge, dashed wedge is below. So here the axial bond is above, equatorial bond is below. Means here the hydrogen is below, so equatorial bond is hydrogen. Now what is the next? You just move on. So this carbon is the second carbon, I say suppose. So at this carbon, the group which is below is CH3, that is axial is CH3. Then equatorial is hydrogen. And at this what is now? We have hydrogen and the axial and equatorial bonds like this. But axial bond is below. So what is below here? D. What is above? Hydrogen. So this is the same thing what we represented. So it is anti-clock direction. This is also anti-clock direction where to move. So this is 1, this is 2, this is 6 again. So during this what should happen? The groups which are living should be always anti-periplanar. So here when Br is living, because it is a good living group, then always there is a group which can live with respect to this. The CH3 cannot be a good living group. So it cannot live, the hydrogen will live, dehydrohalogenation otherwise. So Br instead of that, sorry, when Br is going, this deuterium which is an isotope of hydrogen which is in completely anti-periplanar diaxial position, this deuterium only can live. So what we see, double bond is formed here, having the CH3 carbon, H carbon, means this carbon is not affected. So Br is lost here, D is lost from here. So you will see a double bond formation at this place like this. Means that hydrogen is here, CH3 is as it is, then Br is lost and deuterium is lost. Both these carbons are having still hydrogens. Suppose hydrogen was going, suppose, then we write a D here. So if hydrogen is here and deuterium is here, so you can't say directly hydrogen will live, because it is a C and D bond is a stronger bond, C and H bond is a weaker bond. We can't say the hydrogen will leave, deuterium will exist. No, because hydrogen is in an equatorial position, Br is in axial position. So this Br and hydrogen which are opposite, above and below, here Br and hydrogen are same. So this Br will leave and deuterium will leave. It's a simple way to say. Means above the plane, below the plane, when you have the groups which are living immediately, they should be axial. Means if I write this in axial, its axial bond will come below. So alternatively, so because this axial bond is above, this axial bond is below, this axial bond is below, this axial bond is above, this axial bond is below, this axial bond is above. So immediately that equatorial positions will change. So if axial bond is above, equatorial bond will be below. So same way, if you just see simply here Br and deuterium, you can simply leave. So that you will get a double bond here. So let us see what is given thing for us. So CH3 and H will not be disturbed. H and CH3 is not disturbed. Deuterium is not existing. Hydrogen is existing here. So your answer will be nothing but now. Think clear for this also. Coming to the next. This one. OCH3 we treated with a particular, let us say it is like a passage type question. So there is A, B, C are there. We are getting a final product which is after aromatization. Okay. So now what are A, B, C might be asked in the process. So let us see what are they maybe. What is this process we say? OCH3 is a plus M group, R plus R group, ring activating. This is an acid anhydride. So what anhydride it is? Succinic anhydride. In presence of AlCl3, it's nothing but Friedel-Crafts acylation process. But if it is a bulky, that is an let us say what you call it as acyl group. That acyl group should not come to the ortho mainly, it will come to the para position. So where you will see this acyl means this carbon carbocation will form because oxygen of this is coordinated to AlCl3, then this pi bond will shift, sigma bond will shift in between them. Okay, so that you will get a CO plus at any particular place here or there. Then that CO plus is substituted at para position to OCH3. Then this will become nothing but the loss of hydrogen will be there, because during the aromatic electrophilic substitution, the hydrogen is lost of the benzene ring as a H plus to retain aromatic character. After electrophilic addition, it loses aromatic character. Then to retain aromatic character, the H plus was lost. That H plus immediately comes to this COO minus. So AlCl3 is a Lewis acid, it will leave. So what you will see here is A has to be now OCH3. At para position, you will see C double bond O, but the carbon chain is C double bond O, CH2, CH2, COO minus, or CH2, CH2, C double bond O, OH. So this has to be A. So what is given A here? So this is given with OCH3, this is at ortho position. This is anyhow directly in the ring which we formed, that is not a possible case at this stage. But this OCH3 and this C double bond O is in para position. So your option is C. Anyhow, all the other products that we see. Now after that, we treated with concentrated H2SO4 and heated. So the acid group, that OH group is again becoming like a good living group type. This OH group leaves and this carbon will get a positive charge. So when this is treated with concentrated H2SO4 and heating, it will form again the acyl group at this position. So when the acyl C double bond O is formed, again there is an internal reaction. But that internal reaction cannot happen at this ortho positions. It happens only because of the ring structure, it happens only here. That means what we see? There is OCH3. Here we got a C double bond O. Another C double bond O is here. So what is the ring size now? 1, 2, 3, 4, 5 and 6 again. So you can write another 6-membered ring here like this. But this is C double bond O. This is C double bond. Or this is our B. Nothing but. So this is the B. But okay, the way you write that you should see. So what is that now? Let us say B option, which is I think given in this. So what is B? So they gave us OCH3 at para position C double bond O is there, CH2, C double bond O. So this is A. A is the option for us. But this is at ortho, this is, so first it is not happening at ortho. That's why this cannot be our position. If it is that furnished initially is at ortho, which was the major at that stage, then this can be your option for the B compound. But here, anyhow, that is not a possible case, C double bond O exists. Then after that, what we have done? This compound we treated with zinc amalgam and HCl. So it is nothing but already we know that is a Clemmensen reduction. So when the Clemmensen reduction happens, what will happen? This C double bond O converts into CH2. So what is your C may be? This may be your C. Then after that we are heating with selenium, then aromatization takes place. What is aromatization? Selenium under heating, heat selenium and heated. So if you take this compound and add selenium and heat it, selenium will absorb the hydrogen, remove the hydrogen. So it will remove the hydrogen from here, double bond you will get here. You will remove the hydrogen from here, double bond you will get. So that aromatization takes place. So that you will see the final product as like this. Not this one. So this one was not the case because it is anti, there is OCH3 position changes. So this is anyhow not a C also, sorry. This is not a C also for us because the OCH3 position is different. So you are seeing actually your C compound is like this. So I write in the next page, let us see. So what is C? This one OCH3, or we write OCH3 here, otherwise better we write as it is. OCH3 at this place. So that your compound looks neat for us. So it's only just wait what we see. So this is our C actually. Now when this was heated with selenium, it is losing the hydrogens and getting double bond in the rings. So we see this thing. So this was actually given as your final product. So what is C? This is our C. So this is like a next COCH3. So this is directly the C option again. Okay. So this is how that one a chain of process we are using to convert into that. Clear? Next. This is an interesting where we just use basic applications like this. NBS. So during the NBS reaction, the process is nothing but allylic halogenation or bromination, N-bromosuccinamide. So when we see the N-bromosuccinamide is reacting allylic carbon, hydrogen is replaced with bromine. So where you will see that allylic positions here. So in this compound where we see the allylic. So this is double bond like this. What are allylic positions here? So what is allylic meaning? Double bond adjacent carbons are called allylic. So what are allylic positions here? This position is allylic. Means you can get radical here. You can get radical here. Because this is also allylic position. This is also allylic position. So double bonded alpha carbons are called allylic carbons. But during normal radical, there is no rearrangements. Allylic radical, when it is formed, it can undergo rearrangement because it is just resonance. So there is just a normal hyperconjugation also exists in case of tertiary or secondary, but that radicals will not rearrange. It's only they show hyperconjugation. Means you have suppose CH3, CH radical is formed. Suppose we have CH3, H and CH3. There is a secondary carbon. This carbon is a tertiary now. But hydrogen will not rearrange to convert into tertiary. This type of radical rearrangements will not happen. So which type of radicals can rearrange, or which we actually not saying a rearrangement, it is a resonance actually. Because this pi electron cloud can move like this. But this is a hyperconjugation, that is your existing structure is resonance structure. But hyperconjugation is a pure hypothetical type. It's only just hydrogen sigma bonded electrons are converting. So this type of radical rearrangements will not happen. So this reactions doesn't take place. So this type of tertiary radical, secondary carbon radical will not convert into tertiary radical. But when we consider this type of a thing, what is you are getting? This pi electron cloud can shift here. This pi electron cloud can shift like this here. This pi electron cloud can shift like this here. So what are the total possible cases what we get to see? Means you can see the bromine here. So what are the first? Let us write individually. Double bond is here, CH or C radical here. What is its resonance structure now? What we see? So we will see this pi bond suppose shifted like this here, towards this. Then you will see the radical formed here. So double bond exists outside. Then this carbon will have a radical. But this is converting into Br. Means you can get this compound. You can get this one is converting into Br, bromination process. Double bond you can get here. So we got first, let us say this is one, compound 1. Let us say this is compound 2. We compare later whether the compounds are same or different, we compare. Now coming to the next other radical, allylic radicals that exist. So what is that other allylic radical that exists? Let us write here only. So let us remove this thing which is not. So what is the other allylic radical that we see? You can get radical here. Means already a double bond was here and radical we formed. What is its resonance structure that we see? That is double bond comes here because the pi bond is shifting like this. Then you will get a radical here. So that this is converted to halogenated product. This is converted to halogenated product. Okay, done. So let us take again these compounds as 3 and 4. So this is 3, this is 4. What is the other possible cases that we got is here? Allylic carbonate this. So what is the third one what we are getting? Let us see the other thing. We got a radical here, double bond is like this. Then this can resonate again like this. So you will see double bond formation here and radical is here. So this can convert into halogenated compound Br. double bond is here only, CH3. Also converting, but double bond is here, Br is here. So let us say this is now 5 and this is 6. So among this, like, because anyhow they asked in the question that we require only structural isomer, exclude stereoisomers. So excluding stereo. So even we count stereo also, let us see. So do we have any stereo aspect in this? Or first let us see this thing, then we will come to the stereo part. Among these compounds, any compounds, is it same or different? Suppose first one, anyhow Br is outside the ring, this is a different one. So one simple thing. Then double bond is outside and Br is in the ring, this is also different, separate. Then this one. What is numbering system you do generally? We always start with the double bond given more preference. So double bond should be given 1, then substituents should be given preference later. So if you start here, this becomes 1, then 2, 3, 4, 5, 6. So what are your substituent positions? 1 and 6. Suppose you number different way, let us say giving the double bond preference. So what is I can write? 1, 2, 3, 4, 5 and 6. So what is your substituent positions is? 2 and 3. Is it 1, 6 is correct or 2, 3 is correct for us? Because it is least look and set rule that we follow in the IUPAC system as far as the modern. What is he? Your substituent positions are first one. The first point of difference with the least number is the correct one. So this 1 and 6 is correct, not 2 and 3. So this is correct, this is wrong. So this is 1, 6. Okay. So what is this one? This is also now again 1, 2. You can't number from this side. So this is again 6. So this is also 1, 6. Means both these compounds are actually 3 and 4 are same. 3 and 4 are same. So this is exclusively only a single compound. So 3 and 4 are same. So you have to count these two as a single molecule because they are not different. Now in this 1, 2, 3. So this is 1, 2, 3. So what is this is? 1, 3. Because in the ring you have bromine as well as methyl group. So for the 3, 4, 5 and 6, you are doing the numbering system. And here again it is 1, 2, 3. So we say this is again 3, 3 only. Methyl group and bromine are at 3 and 3. In this case it is 1 and 3. And you can't give bromine preference, you have to give double bond preference. That's why we are saying methyl is getting 1. So how many exclusive products we have? 1, 2, this 3 and 4 as a single, 3, 5 and 6. So how many products we actually have according to our question? Isomeric, monohalogenated also. That is totally 5. That is excluding stereoisomers. So if you include stereoisomers, means stereoisomer means you will count there is maybe a geometrical, there may be an optical things. So do we have any optical isomers or geometrical isomers here? Do we have geometrical isomerism here? No. Do we have any optical isomer? Means is there any chiral carbon? No. So this is only a single molecule. So this is only one. Do we have any geometrical isomerism here or optical isomerism is here? Because geometrically is not possible because it is CH2. Because terminal is two hydrogens are there. But this carbon with Br and hydrogen in the clockwise and anti-clockwise, the groups or directions are same. So this carbon is chiral carbon, we say. So this has two total. D and L pair. Now here, do we have anything again like that? So whether you count this or whether you count this as one and same. This carbon is again, I can say chiral carbon. So we have in the 3 and 4 also two molecules, D and L. So geometrical isomerism within the ring that doesn't exist. Okay. Next, coming to this, do we say this carbon is chiral? Yes. So in this also we have two, D and L. Do we have in this? So this one has CH3Br, this side CH2 like this side CH. So this carbon also becomes chiral now. So this also has two. So again it is D and L. So overall how many we had? This one is only a single. The second one has an optical activity, third one has an optical activity, fifth one has an optical activity, sixth one has an optical activity. Means among the 5, 4 molecules are having their optical activities. So this 4 by 2 times, so totally 9 including stereo here. Okay. So this is totally 9 with including stereo, without stereo 5. Okay. Coming to the next thing, next slide will be mostly for us it is an empty. The next, total number of alkenes possible by dehydrobromination, removal of H and Br by 3-bromo 3-cyclopentyl hexane. So we have what is the basic structure of that carbon? See, 6 carbons, hexane, 3-bromo 3-cyclopentyl. So at the third carbon we have bromine as well as cyclopentyl group. So he is asking how many alkenes we may get by the dehydrohalogenation of this. So whenever there is a product are asked, number of alkenes are asked, number of suppose alcohols are asked, any compound is asked, products are asked, we have to always consider by default stereo. So even if you are having a possible stereo isomers, you have to count them. But what he is saying is with ring expansion is also there, possible by a dehydrobromination with a ring expansion that should exist. So what do you see? First the Br, which is a tertiary carbon, this can leave easily. So first what is with the Br loss? We see this C positive. But 4-membered ring having a positive charge in the alpha position, 5-membered ring having an alpha position positive charge, immediately the ring will expand. But 3 with the positive charge generally, because cyclopropyl methyl carbocations are more stable. So with the 4-membered ring having a positive charge or 5-membered ring having a positive charge, rings will expand. Ring expansion takes place. So this carbon bond will shift towards this, or this carbon bond will shift. So what you will see? because he is asking with ring expansion. Otherwise, from this directly you may get an alkene. How many alkenes you may get at this? You may get double bond here, you may get double bond here, you may get a double bond here. So, without ring expansion, before ring expansion, we got 3 basic alkenes without ring expansion. What are this? Because anyhow ring expansion happens and finally you will get a more stable product. That is the final thing, that's okay. But any carbocation, whenever it is existing, that carbocation immediately results their respective alkenes there. So, let us write that, then we will proceed. So, ring expansion, before ring expansion. Before ring expansion, what should exist? You may get double bond here, you may get double bond here, you may get double bond. Means you will see double bond like this. You may get double bond like this. You may get double bond this side. So, these are the first 3 alkenes that we got through the carbocation immediately resulted. But if suppose we already said there is a number of alkene, alls, star alcohols or star alkyl halides or star anything is asked, you have to count even that particular product, particular compound which is giving any stereoisomers. Means you need not say there include stereoisomers. Even if they don't say include stereoisomers, you write when the number of products are asked, number of alkenes are asked, we write even including the stereo. So, when they say exclusively or they specifically say like this, include, exclude, then only we may include, we may exclude. Otherwise, when number of products is asked, simple thing, we should count even stereo. So, in IIT that point you just take care, because they say number of alkene or alcohols, they just always count that also. So, is there any geometrical isomerism possible at this? Yes, because at this carbon we have CH3 and H. Here we have isopropyl and propyl group, sorry, pentyl, cyclopentyl and propyl. So, this carbon has geometrical, that is E and Z is. We can't say cis trans. So, E and Z is. In this, do we have any geometrical isomerism? No, because at this carbon, your chain is completely same. So, this is only a single compound. But anyhow, they asked through ring expansion for us. That we will see later. Do we have any possibility in this? So, this carbon has C2H5 and icyclopentyl. This carbon has hydrogen and ethyl groups. So, ethyl and ethyl, so you can have cis trans in this. So, how many we are getting before that itself? 5. If they ask all possible, you have to count even this. When they ask all possible, we have to even count this also. So, now let us do the ring expansion. So, the 5-membered ring having a positive charge will become a 6-membered ring. So, what is after ring expansion is? Suppose after ring expansion, if you see, this is the thing what we see. 6-membered carbon ring. So, this carbon is suppose 1 because continuous chain is like there, because we shifted this carbon to this. So, 1, 2, 3, 4, 5 and 6. Means this CC bond is cleaving, or this sigma electron will convert to this carbon as a negative charge, or that orbitals are pulled actually by the empty orbital at that carbon. So, these carbons which are in the ring, they try to move like this. So, one of the bond between the C and C cleaves, this carbon will go and link to this carbon. Clear? So, that this one is 1 with an ethyl group here and a propyl group there. So, 1 if you see this one, this is suppose 6th, second carbon will have plus. So, this will have plus, but we get now here C2H5 or C and C, we have CCC. Now, this carbon is a quaternary carbon. This is a secondary. So, after ring expansion, this can further rearrange to give more stable, because adjacent immediate carbon is a quaternary or tertiary. When you have a secondary, immediately it rearranges there. So, tertiary is there, secondary becomes tertiary. Quaternary is there, quaternary becomes tertiary. That means among this ethyl and propyl, one of that will shift. Which will shift? Generally propyl group shifts, because more electron denser group will shifts. So, more plus I affecting, more plus M affecting group generally migrates. So, we will say tertiary is better migrating than secondary, secondary is better migrating than tertiary, primary, primary is better migrating than methyl. So, just migrate propyl group. So, you will see ethyl here, propyl here, then positive charge here. So, how many we may be getting here? So, from this do we get any alkenes? At this carbon we can't see any loss of hydrogen. So, we will see only loss of hydrogen from here. So, what is direct alkene that we get from here? With the loss of H plus from. That is, you will see this maybe. Means their intention is to ask now this one also, because there is already ring expansion happened. So, double bond will form here. But this one is rearranging to this which is stable. Now, from here, where hydrogen can be lost? Hydrogen can be lost at this, hydrogen can be lost at this, hydrogen can be lost at this. Means you will see three different alkenes here. What is the first one? You write C double bond. What is secondary? Here or here I will write. So, let us write here, left side. Now, write here, double bond here. But which is major if you say? I will say this is the last one major, because number of hyperconjugatable more substituted alkene. How many hyperconjugatable? 2 plus 2 plus 2 plus 2. 8 hyperconjugatable hydrogens are there in this. How many hyperconjugatable hydrogens are there here? 1 here, 2 here, 2 here, 5. In this 3, 1 and 2, 6. So, this is most stable. So, this is more stable, as well as you can say major. So, let us see again in this, do we have any geometrical possibility? Then do we have any optical possibility? Do we have any geometrical possibility at this carbon? Double bonded set. This carbon has hydrogen. This is completely CH and propyl group is there, CH2. So, this carbon has different groups. This carbon has two different groups. So, you will see at this carbon-carbon double bond center, you will see cis strands. Otherwise, instead of cis strands, do we have? No. So, we say E and Z. So, here EZ isomerism is possible. Means this is two molecules. Now, let us see in this. Do we have, let us say here, this is a double carbon, double bond anyhow, in this ring. So, this carbon is a chiral carbon. So, we have D and L in this. In this also double bond is here. So, do we have any double bond continuation? This is CH2 something like this. This is CH2 something like this. This is propyl and this is ethyl. So, you can say this group is same, this group is same. You can say cis trans. Otherwise, you can use E and Z also. So how many are there in this? 2. How many are there in this? 2. How many are there in this? 2. And so from this final stable carbocation, we got this. Now what is this? It is nothing but now what we say? One more. So total all our ring expansion through, we will get 7. Okay. So if you say all possibles, so here we had 5, here we had 7, totally it will be 12. Okay. So how many, what we are getting with the ring expansion cases? Clear? So coming to the next thing, let us see the next question, one question. So this is like a alkene related now, again addition reactions in electrophilic addition reactions in alkene. With this we just end now session. So what is this? So this is acid catalyzed addition of water. So this is acid catalyzed addition. This is simply we say OMDM. This is hydroboration oxidation. This is just an addition of chlorine in water, nothing but HOCl. But acid catalyzed addition follows Markovnikov rules. You can say simply MR. And reaction proceeds through rearrangements. So rearrangement also exists. So formation of carbocation will be there. After that, that carbocation can rearrange there, because pure carbocation we are getting there. But here we will get a cyclic, we are getting a cyclic intermediates. So this one is Markovnikov, MR, but no rearrangement. This is also anti-Markovnikov rule without rearrangement. And this is again without rearrangement, but it should follow again Markovnikov rule. So what is in this OH minus and Cl plus type? Because your Cl is an electrophile there in the HOCl because of presence of empty orbitals. So we treat that Cl as a Cl plus, not based on the electronegativities or nothing like that. So now what is the option that are given are answers. So here the addition can be done anyway, because OH and OH you can add anywhere because your product is same. But this can be nothing but OH should be added here. So that is what we have done. So this is nothing but again done with through Markovnikov rule. So this is added with Cl, this is added with OH. So that is the product. So the products that is given okay for us anyhow, that they last, but anyhow the basic thing is you have to match with this process. It involves a neutral electrophile. So is there any neutral electrophile in this process? No. Because what is your electrophile in this process is H plus acid. Then what is your water is nucleophile there. Clear? So P will not come for this. Let us see any other options for first option. So first it won't involve a neutral electrophile. Next. Involves free carbocation. Yes. So Q stands for this. So for A, you can say Q, right here. Involves a cyclic intermediate and a transition state or transition state. Transition state can exist anywhere actually, because loss of bond or cleavage of bond, there is a transition state. Rearrangement is there, there is a transition state. So each and every step has a particular transition state. Clear? So through transition state, anywhere the transition state exists, even a process which is a single step process, even a transition state exists. So you can take R also for this. Then product formed will be D and L pair. So can we say this one is a DL pair? No, because this here carbocation was formed here, then hydrogen shifted from here to here, then this carbon is having a positive charge. So OH group can come, or water can come from above, water can come from below. So because the planar carbocation is there, but methyl groups are there at the two sides. So this carbon is not a chiral. If one of that is suppose something other than CH3 and CH3, one of that is suppose something else, then this carbon will become a chiral carbon instead of C2H5 again, because this side we have C2H5, CH3. So this might be a isopropyl group, or maybe a propyl group, something like that, or benzene related thing. Then you can say this carbon becomes a chiral, then this compound will become a DL pair there. So DL pair you won't get in this. Water acts as a nucleophile in one of the steps. Yes. So water is a nucleophile here. So you'll say T. So QRT in this case. Next, let us see this. OMDM. So involves a neutral electrophile. But what is your electrophile? HgOAC plus Hg plus OAC, because OAC part is leaving. That will form a cyclic intermediate. So pure carbocation will not form. So cyclic intermediate exists, because whenever any electrophile has a lone pair, it will exist like a cyclic intermediate. It won't exist like a planar intermediate. So R exists for this. Clear? Next, there is product formed is a DL pair. So this carbon will become a chiral carbon now, because H is there, OH is there, CH3 is there, and ethyl group is there. So this will involve DL pair there. And water acts as a nucleophile in one of the steps. Yes, because here you have water that attacks and converts into OH. So that is also exist here. So OMDM process you just go through first. Where water is there, then it will attack that cyclic intermediate. Then that carbon will become like OH carbon. So water is your nucleophile in this process. Next, coming to the diborane, HBO, hydroboration oxidation. Diborane is a neutral molecule. So it involves a neutral intermediate, neutral electrophile, sorry. So this you will say P. It involves a formation of a free carbocation. No. The reaction doesn't go through the carbocation, because there is no rearrangement. If carbocation was there, then there is a possibility of rearrangement maybe. So carbocation will not exist, cyclic intermediate exists. So you can say that is also there for this. Next, R. The product formed is a DL pair. So this compound is not a chiral carbon, doesn't exist in this. So this compound is not having a DL pair in this. So S will not. Water acts as a nucleophile in one of the steps. Here we don't have any water content in this process. So anyhow that will not exist. Okay. Next. In the chlorination, means this one, addition of HOCl. So you are saying the Cl is electrophile, that will form a cyclic intermediate here. So you don't have a neutral electrophile in this, or S. Neutral electrophile is chlorine, so that also stands for here, P, because it will form a pi complex first before converting into a cyclic intermediate. So your chlorine itself is an electrophile there. So it's a neutral electrophile there. Next, it involves a free carbocation. No, it forms a cyclic intermediate again. So again this R stands for here. Then product formed is a DL pair. So do we see any chiral carbons here? Yes. So this carbon is a chiral carbon. So the product formed is having a DL pair. So that is also correct. Water acts as a nucleophile in one of the steps. Yes. When there is a Cl, then water is actually reacting. So it is not HOCl we added. it's actually we added Cl2 plus water. So we say generally the HOCl addition. So OH and Cl are effectively added here. So water is acting as a nucleophile at this cyclic carbocation when it is formed. So that is T also exists. Clear? So these are the things for the particular process. Okay. So hope everybody is preparing well and utilizing the classes. So prepare well. All the best. We'll see in the next class. So we are actually concluding this session with this. Okay. Thank you.